Picture this. It's a totally normal spring morning, and one of the most advanced power grids in the world just starts to tear itself apart. This is the story of how that happened, second by second, based on the official investigation.
Right around 12:33 in the afternoon, the unthinkable happened. The lights just went out, not in one city, not in one region, but across the entire Iberian Peninsula, a complete blackout.
In a split second, Spain lost every single watt of its electricity. We're talking over 25,000 megawatts of power. Just poof, gone. To give you an idea of how much that is, it's enough to power tens of millions of homes. And let's be clear, this wasn't just some big incident. This was a historically massive failure. It was, in fact, the most severe blackout the entire continent of Europe had seen in more than 2 decades. So that brings us to the million-dollar question, right? How on earth does a modern, sophisticated, interconnected grid like this suffer such a total catastrophic collapse? Well, you can bet the alarm bells were ringing. Immediately, they assembled a team of 45 specialists, the best of the best from all over Europe. They dug into thousands of data points, and everything we're about to walk through comes directly from their first factual report. The very first thing the investigators had to do was officially classify the event. And, well, its official designation is pretty sobering. On what's called the Incident Classification Scale, this was a Scale 3. What does that mean? It means there is no Scale 4. This is the highest, most severe level there is. It's the official term for a complete and total system collapse. Now, here's where it gets really fascinating. This collapse didn't just happen out of the blue. The data shows the grid was sending out distress signals for more than an hour before it finally failed.
So, what were those first warning signs?
What did the investigators find in the hours leading up to the disaster? The answer came down to one specific phenomenon: grid oscillations. Okay, so what in the world are grid oscillations? The easiest way to think about it is to imagine the entire power grid is like a giant, perfectly tuned guitar string. A little vibration is normal, no big deal. But these oscillations, they're like that string starting to wobble wildly out of control. And if it wobbles too much, that string is going to snap. And you can see how this escalated over time. At just after 11 in the morning, things are fine, just some minor, safe wobbles. But then, at 12:03, a new, stronger wobble appears. Then comes the critical moment at 12:19. A system-wide oscillation starts up. That was the real red flag that the entire grid was becoming dangerously unstable. So let's dig into these wobbles a bit more, because not all wobbles are created equal. And understanding the difference between them is absolutely key to understanding why the whole thing came crashing down. That first oscillation at 12:03 was what you'd call local. Think of it like a single piston in an engine rattling out of sync. It's a problem, but it's contained. But that second one at 12:19, that was inter-area. And that is way more dangerous. Now we're talking about the entire engine block shaking itself to pieces, with the whole Iberian Peninsula vibrating against the rest of Europe. Now, the grid operators saw this happening. They weren't just sitting on their hands. They took action to try and damp down these oscillations. But here's the fatal twist, and this is a direct quote from the report. The very actions they took to stop the shaking had an awful unintended consequence. They caused the voltage across the system to climb to dangerously high levels. And that brings us to the climax. The system is unstable, it's shaking violently, and now the voltage is sky high. At 12:33, it finally reached its breaking point. What happened next was just a lightning-fast chain reaction, a cascade of 5 separate critical failures that took down 2 entire countries in less than 30 seconds. Let's walk through that domino effect. First, the voltage spiked, hitting over 450 kilovolts, which is way, way over the limit. That tripped the first power plants offline. Second, with those plants gone, there wasn't enough power being generated to meet demand, so the grid's heartbeat, its frequency, started to plummet. Third, because its rhythm was off, the Iberian grid lost sync with the rest of Europe. Fourth, protective systems did their job. They sensed the danger and automatically severed the power connections to France to save the rest of Europe. And fifth, now completely isolated, unstable, and massively imbalanced, the entire Iberian grid just collapsed. The collapse took just seconds. The recovery? Well, that was anything but. The monumental task was now ahead of them. How do you restart an entire nation's power grid from absolute zero? The process started just 1 minute after the collapse, using special black start generators and getting a helping hand from France. But this wasn't like flipping a circuit breaker. It was a slow, methodical, painstaking effort. It took nearly 12 hours to get Portugal's main grid back up, and over 15 hours for Spain.
And you know what's incredible? The grid's own defense plan tried to stop this from happening. Automatic systems actually cut power to over a third of the country. That's more than 8,500 megawatts of demand, in a last-ditch effort to rebalance everything. But the cascade was just moving too fast. Even that wasn't enough. So we know what happened, but the investigation is far from over. This factual report is really just setting the stage. The big question is, where do they go from here? The expert panel has the timeline locked down. Now, the real detective work begins. They have to find the ultimate root cause. They're going to scrutinize the voltage control systems, and they're going to analyze the behavior of every single actor on the grid that day, from the biggest power plants to the individual operators. And really, this is the most critical takeaway from the whole thing. This massive investigation isn't about assigning blame. It's about learning from this failure to come up with recommendations that will make the entire European power system stronger and more resilient, to help make sure this never happens again. You know, an incident like this is a huge wake-up call. As our energy system gets more complex with more renewables and intricate controls, the challenge of keeping the grid perfectly stable gets exponentially harder. And it leaves us with this one central question for the future. How do we engineer a grid that isn't just clean and powerful, but one that's unbreakable?